Good morning. So welcome to day 2 of the ICRP Symposium. For those of you who weren't up early yesterday morning, I'll remind you I'm Chris Clement, Scientific Secretary and CEO of the International Commission on Radiological Protection. And this morning we have a really special treat. For those of you who are Canadians, our speaker needs no introduction. From those of you from abroad, I'll read his a short bio on Bob McDonald, who is host of CBC Radio's Quirks and Quarks. Before I read what's been prepared, I want to say that I've been listening to Quirks and Quarks for as long as I can remember, maybe not as long as I've been alive, but nonetheless a long time, and always enjoyed it. It's a fantastic radio show, my favorite radio show on CBC, which is Canada's national broadcaster. So Bob McDonald is, it says here, one of, but I say the Canada's best known science journalists, bringing science to the public for more than 40 years. He also, in addition to hosting Quirks and Quarks, which is the CBC radio show, the award-winning science program that is heard by 800,000 people each week, Bob is also a science correspondent for CBC TV's The National, which is our big news show, and host and writer of the children's series Heads Up. Bob has been awarded, or is an officer of the Order of Canada, and is a recipient of the Queen's Jubilee Medal. Bob has been honored with the Michael Smith Award from the National Science and Engineering Research Council, the Sir Stanford Fleming Medal from the Royal Canadian Institute, and the McNeill Medal from the Royal Society of Canada. He also won a Gemini in 2008 for the best host in a preschool, children's, or youth program series. I understand Bob's also very proud that in 2015, asteroid 332324, which everyone knows, I'm sure, was officially named Bob McDonald, all one word, in his honor by the International Astronomical Union. Last but not least, Bob holds 12 honorary doctorates. I don't know anyone who has that many. So please welcome Bob McDonald.
Well, thank you very much, Chris. The picture is hilarious that they just showed you there. You might notice that I dye my hair gray now. It's very expensive. It costs a lot to do this. And Chris mentioned I've been 30 years as the host of Quirks and Quarks. We just celebrated my 30th anniversary there. And believe it or not, next year, 2023, will be my 50th year since I started communicating science to the public when I joined the Ontario Science Centre in Toronto, one of our large science museums. So boy, do I feel old. Man. Although I have to say, I had an elderly couple over for dinner the other night, and after dinner, the husband said, you know, we went to a really good restaurant the other day. You should check it out. I said, sure. What's it called? And he went, oh. What do you call that flower, the red flower with the thorns on it that you give to somebody? I said, a rose? Then he turned to his wife and he said, Rose, what's the name of the restaurant we went to the other night? Yeah, we all suffer that. As a science journalist, I've been covering the environment for a very long time. In fact, my first job at the CBC was in 1978 when I was asked to do a documentary on climate change. Climate change, 1978. And back then there was a debate. It was called running hot and cold. Because on one side, the geologists were saying, you know, we've had 5 ice ages with warm periods between them that last 10,000 years. And it's been 12,000 years since the last ice age, so we're overdue. We should be getting colder. But then the climatologists were saying, no, now we're putting these greenhouse gases in the atmosphere. It's going to override that. Well, we know who won that debate. And it's been amazing from my perspective to watch all of the predictions that the scientists were making back in the 70s come true. The loss of ice in the Arctic, stronger hurricanes, droughts, water shortages, loss of biodiversity, blah, blah, blah. And it's all come true. In fact, it's come true faster than they predicted. And if you do enough of these stories, you start to get a little depressed because it's all bad news. Now, I don't want to minimize the problem. It's very serious. But I thought, okay, we've been pointing at the problem for decades. What's the solution? How do we move ahead? And when I started looking into it, what's the green technology, I came to the wonderful discovery that all the technology to go green already exists. There are no new inventions needed to go green. They're all out there. So I put them together into this book called The Future Is Now, which just came out. And for the last 4 weeks, it's been on the bestseller list in Canada. I'm quite happy about that. People like it because it's positive. It's positive. So the thing is, we know how to do this. We know how to capture energy that falls out of the sky. We know how to capture the wind. We know how to capture the heat out of the ground. We know how to store energy. It literally grows on trees if we want that. And then we're going to be rethinking nuclear and both fission and fusion, which I know you know a lot about, which I'll be talking about in a second. So I just put these all together into the book to say, here's the latest. Here's the update on where it all is. Plus, I put in some personal stories of sailing experiences where I've experienced the power of the wind when I got caught in a storm, getting stuck underneath a rock in Hawaii when I was snorkeling, and I discovered the power of wave energy. So I've done things like that as well. So if all this technology is out there, why aren't we using it? Well, we had a good example just over the last couple of years of how society can deal with a threat to humanity and how we beat it. And that threat, that invisible threat, was a virus. Here was something we could not see that was killing people by the thousands. And 4 elements came together to beat it: science, technology, the government, and the public. And we all bought into it. We all bought into it. But something else happened as a side effect. When we all shut down, we stopped driving cars and trucks. We shut down industry for a while to prevent the spread of this airborne virus. An amazing thing happened. Skies went clear. Carbon emissions in cities disappeared. This is China before and after, showing carbon emissions. Here's the northeastern United States, the industrial sector. Same thing. Carbon emissions went down. Skies turned clear. And these emissions went down in a matter of days by quite a lot. By quite a lot, 35%. And not just carbon dioxide, sulfur dioxide, nitrous oxide, the stuff that comes out of tailpipes and smokestacks. Skies over cities like India, New Delhi, that had been polluted for decades suddenly turned blue. And this happened all over the world. And this is good news. As soon as we stop putting our garbage into the air automatically starts to heal itself. What a wonderful news. But that showed the scale of what we need to do to stop the climate from getting warmer. We got to really reduce our emissions. So how do we do that? Well, the science. The Chinese scientists, to their credit, as soon as they identified the coronavirus, they sequenced its genome, its genetic sequence, and they sent that out to the world. And there was an enormous international effort to find out how this virus works, how it infects the lung cells, how it spreads, and how we can develop vaccines for it. Then industry came along and said, yes, we can develop vaccines, several different kinds of vaccines, and put out billions of doses to spread around the world. So the industry, the second element, was there. The government came in. This is our chief medical officer, Theresa Tam in Canada. She's our federal medical officer. The government came in and said, one, we're going to make billions of dollars available to support the industry, to support those who lost their jobs temporarily when we locked down, and to support companies that were losing during the lockdown. And they said, here's what we need to do. We need to change the way we act. Wear masks, wash your hands, social distancing, all of that. So the government's on board. The public? Well, most of us bought into it. Not all. There was a small minority of very vocal people who didn't want to do it and who put out misinformation about vaccines to try to confuse the public. But they were a small minority. The rest of us bought into it. And look, here we are, back in person. No longer talking by Zoom. Isn't this wonderful to be in face-to-face again? Wow. So we did it. And what did we do? We flattened the curve. We flattened the curve more than once, and we're still doing it now. Okay, so it worked for COVID. It worked for COVID. Science, technology, the government, the public, billions of dollars, and we did it in 2.5 years. How remarkable. Okay, Here's another curve we need to flatten. This is the climate I've been talking about. The last 500,000 years of the Earth's climate showing the ice ages and the warm periods. How do we flatten this curve? Well, the science is there. They've been telling us about this for decades. The technology's there. We know it's there. What about the government and the public? Well, right now, there's another United Nations Climate Change Conference happening in Egypt. The 27th meeting. I was at the first one. Rio, 1992. And everybody said, yep, this is a big problem. We're going to set targets. Then the targets aren't met. So they have another meeting. They say, okay, well, we'll move the targets a little back. And they keep doing that and keep doing that and keep doing that. So while there has been progress, bottom line is the emissions are still on the way up. So the governments are not totally on board. The public, well, one person in particular is kind of angry about this. The youth are afraid. They're angry and they're afraid because it's their future. And there is a very small minority of people who like to spread misinformation about the climate and confuse the public and confuse the politicians. So we don't have those other two elements in place yet. So how are we going to go from here? Well, the first thing we need to do is to get over the big elephant in the room. The big elephant in the room. And I'm not making an enemy out of the oil companies. In fact, I don't want to point fingers at anyone. I don't want to say, it's all your fault, oil companies. It's all your fault, government. It's all your fault, industry. Because if we do that, if we start pointing fingers and make enemies, nothing happens. Because you have the good guys and the bad guys, the white hats, the black hats, the evil oil empire and the good tree huggers. And when you do that, everyone just digs in and nothing happens. Instead, let's cooperate like we did with COVID. Let's cooperate. And we're not going to put the oil industry out of business because oil is amazing. Oil has so much energy in it. It's so dense. And you can use it for so many different things. It drove the Industrial Revolution. Let me give you an idea of how much energy oil contains. There's a unit of work called the joule, which is 1 kilo raised 1 meter. That's a joule. 1 kilo, 1 meter. So how much is in a standard barrel of oil? 6.3 billion joules. Now that's hard to get your head around, but how much is that? Here's another way to look at it. The Great Pyramids of Egypt, somebody actually figured out how many joules it took to build the pyramids. Just the mass of the stones and how high they had to be lifted. It turns out to be 2.4 trillion joules. Again, big number, hard to get your head around. But how many barrels of oil would it take to build the pyramids? 400. That's one oil well in one day. You can get that out of one well in one day. 400 barrels to build the pyramids. And when you look at all the energy that we use in the world every year, all the countries around the world, our total energy consumption, and turn that into pyramids, we burn about 2 million pyramids a year. 2 million pyramids a year. It took the ancient Egyptians 20 years just to do it once. So we are so awash in energy. There's so much energy in fossil fuels that it's incredible. We're not going to let that go easily. And the problem is not the fossil fuels themselves. It's how we're using them. It's how we burn them. I mean, you think about it. A fossil fuel, you dig it out of the ground and you light a match, and it goes boom. That's it. Coal is a rock that burns. It's a rock. You can take it and just put a match on it. You don't have to do anything to coal. But that's the problem. Burning it is probably the worst thing you can do because we call them hydrocarbons because they're long chains of carbon with hydrogen atoms stuck to them, like Christmas bulbs on a string. And when you plug in your Christmas lights, it's the bulbs that come on. So it's the hydrogen that's coming off that's giving us the energy. The carbon is left behind. So the carbon by itself, smoke, soot. Or the carbon will combine with oxygen, carbon dioxide, carbon monoxide. If there's sulfur, sulfur dioxide. So it's the leftovers. It's the leftovers that are the problem. So here's an idea. Why don't we just take the hydrogen out? Just use the hydrogen, leave the carbon behind. And there's a company here in Canada, just east of here in Saskatchewan, that has figured out a way to get hydrogen out of oil while it's still in the ground. They take 2 oil wells. Down one, they put steam and oxygen. There's a reaction with the oil, reforming, and hydrogen bubbles up the other one. So you just use the hydrogen. We can also get it out of natural gas like we are now. So the oil companies could switch to hydrogen. They could, and they're doing this. They could say, we're energy companies. They're just going to give us a different product. And we could do that. And hydrogen, when you burn it, it's totally clean. So there are already hydrogen fuel cars. Toyota makes one called the Mira. And here in Vancouver, there are some prototype fueling stations, and they're experimenting with that. Although, I think we're going to see hydrogen come first to buses and delivery vehicles, because they all come home to the same place every night, so you only need one fueling station. We don't have an infrastructure for hydrogen yet, but it's coming. It's coming. Airbus Industries is making hydrogen aircraft. They're going to have engines that are hybrid. They're electric with hydrogen supplements. So they're both hydrogen and electricity. They're making a small jet, and they're making a futuristic called a blended wing. This is great, because the airline industry contributes a lot to carbon emissions in the atmosphere. They want to cut that down. Now, there's only one little issue. One little issue. Hydrogen is a great fuel, but it takes up more space, so you need larger tanks. Now, normally in an aircraft, the fuel is in the wings. Well, they'll do that with the hydrogen planes, but they'll also need another tank within the fuselage where you sit. So how would you feel getting on an airliner knowing there's a big tank of hydrogen right behind you? I know what you're thinking. What about the Hindenburg? It's going to blow up. Ah! This is a public perception problem, because hydrogen is actually a safer fuel than gasoline or jet fuel. Because when you get a leak of hydrogen, it goes up. It's lighter than air. It just disappears into the air. A lot of airlines, when they have a crash, the people actually survive the crash, but then they get incinerated by the fire because the jet fuel goes down. It stays on the ground, and it burns the plane from the bottom up. Hydrogen goes up. And believe it or not, 92 people survived the Hindenburg disaster because the hydrogen fire went up over their heads. It went up into the sky. And as the ship came down to the ground, they just jumped out windows and ran out from under the fire. Those who were killed by the collapsing structure and burning diesel fuel from the engines. That's what killed the Hindenburg people, not the hydrogen fire. So there's a public perception here about hydrogen that we have to get over. And this means education about the technology. And I'll keep coming back to this. It's all about education for the public, for the politicians, to understand how these things work. Electric cars, you're probably noticing a lot more of them on the road now, and they're not all Teslas. They're not all Teslas. Ford took its iconic muscle car, the 600 horsepower Mustang powered by a big V8, and turned it into an electric car. Of course, you can still get the muscle car if you want it, but they turned it electric. That was very brave. And all the car companies are doing this, so that means the cost of electric cars is going to come down as the big companies get into it. Of course, the big problem is batteries. Where are we going to get the batteries? Currently, they're lithium-ion. They use rare metals, and there's issues with where that stuff comes from. But however, there's an enormous amount of research right now on other battery technology, solid-state batteries. Toyota's looking at those. They're very thin, lightweight. Batteries made of different materials. There's even a battery I heard about that's made of iron, and all it does is rust. And you get electricity out of it. So there's a lot of work going on in batteries right now to make them lighter, make them last longer. So watch out for that. It's coming. Let me just skip through. We're all familiar with solar energy. The thing about solar is that once you set it up, that's it. There's a cost up front, but then you don't do anything to it. It just sits there taking in the free energy of the sun. Unlike oil, that you use it once, you blow it off, and then you got to keep digging it out of the ground. But solar energy, that's it. Same thing with wind. These black silicon panels, they're becoming cheaper. In some parts of the world now, solar is cheaper than coal because the cost has come down so much. But there's another variation on solar besides these big farms and what you see on rooftops. India, for example, and California are looking at putting solar panels over canals because they have a lot of irrigation canals, thousands of kilometers of canals. So you put them over there instead of covering agricultural fields. But here's another technology. They're called perovskites. And it's another class of material that are solar voltaic, but you can print them into really thin films, so thin you can actually see through them. So you could put these things on windows. And you think about all the windows that are in our cities on the tall buildings that face south. That's a huge area. And all those windows could be solar voltaic, but you could still see through them. There's an idea to make perovskite paint. So all you do is paint your house. Paint your house, and it's solar. How neat. And there's an even crazier idea. Put perovskite paint on the inside walls of your home or a building like this. So when you turn on the lights, some of the light will be absorbed by the walls and turned back into electricity. Recycling light. What a neat idea. So solar energy is going to evolve to the point where you won't even see it. It'll be incorporated into the architecture of buildings. It'll be in the building materials, the paint, the windows, everything. So it won't just be these big. So there's really interesting stuff happening with solar. Wind, we've been capturing it for centuries, up and down the Nile, crossing oceans. Holland built itself. I'm a sailor. I get to feel the wind all the time. And then as here in North America, as people moved towards the center part of the country, before electricity was there, they had these windmills that both pump water and generated electricity to keep the lights on. But now we've settled into this three-bladed design, and that's the most efficient and easiest to manufacture, well-balanced. But this technology is changing as well. It's going big, because in wind, size matters. The larger you are, the more air you catch. And because the windmill is prescribing a circle in the air, if you make the blades just a little bit longer, you know that old formula you had to learn in high school, pi r squared? Are you all still there? You're very quiet. Okay. There was an elementary school, and they had a parents' night, and the principal came out and said, "We have little Janie from kindergarten, who's the smartest kid in the class. She's going to tell us what she knows." Little Janie comes out to the stage, stands there in front of everyone, and goes, "Pi r squared." Everybody goes, "Whoa, that's really great for kindergarten." Then the teacher comes out and says, No, that's not right. Pi r round, cake r square. Okay, never mind. That r square is the radius, which is from the center out. So a blade in a turbine is a radius. So if you make it twice as long, you get 4 times the area. You square it. So that's why these things are getting so big. And they're getting so large. The largest at the moment is called the Haliade X, 12 megawatts. 12 megawatts. A single turn of the blade can produce enough energy to run a house for 2 days. Just one turn of the blade. And they're saying it can run like 15,000 homes. So instead of just one of these, you'll have, or instead of a field of them, you'll just have a few. Almost the height of the Eiffel Tower. And for our Canadians, 2.5 times the height of the Peace Tower on our Parliament buildings in Ottawa. They're enormous. They're enormous. And rather than put them on land, they're probably going to be offshore. Europe is doing this now. The United States is going to do it on the East Coast. We could be doing this in Canada, but we're not. So wind is just going to go enormous to really, really large. Let me just quickly go through a couple of others. Put the same technology underwater. You got tidal energy. And here in British Columbia, we have a lot of islands. And whenever the tide goes between islands, it speeds up, and you get very strong currents. So you can take the tidal energy that we could be doing. But rather than put them underwater, you can also put them on the surface. This is an experiment on our east coast in Nova Scotia, and it's a floating tidal generator. It's basically a boat that you anchor with big propellers on the back, you lower them down, and the tide runs the props, and they generate electricity. The advantage is that if something goes wrong or you need to fix it, you can just lift them up and work on them. In Scotland, they're into this in a big way. Looks like something Batman would drive. But same thing. And you can put these anywhere around the world. So tidal energy, there's energy on the tides. Big question is energy storage What are we going to do when the wind doesn't blow and the sun doesn't shine? Batteries are one way, but they're expensive. They only give you a few hours worth of energy. Here's another way. We could store it in hydrogen if we want. There's a company in Ontario here in Canada that's storing it in compressed air. They're above an abandoned mine. So they pump air down into the mine until it builds up to high pressure. And there's a large volume of it. And they store it there. And then when you need energy back, they let the air come out through a small orifice. It comes out at high speed and spins a turbine. Storing energy in air. Storing it in air. You're familiar with the myth of Sisyphus? Poor fella. He insulted the gods. Don't insult the Greek gods. They don't like that. So his punishment was to roll a rock up a hill every day at great effort, and when he got to the top, the rock would roll all the way back down again. Sisyphus was the world's first mechanical battery. Mechanical battery. Batteries don't just have to store electricity. They store energy. And the rock is storing potential energy, the potential to fall. So there's a group in Europe with a project called Gravitricity. It's the same thing. It's the energy vault. And they are these large concrete blocks that when there's lots of electricity around, they haul them up into a big stack. And when you need electricity, they pick up a block and they let it slowly fall to the ground. And as it's going down, there's a pulley at the top of the crane that spins and generates electricity. And there's 5 of these, so there's always one falling. Storing energy in gravity. Here's a group in Norway. They store energy in sand. Sand. You've probably been out on a beach in the tropics. You forget to put on your shoes. You burn your feet on the sand. Sand can be heated up to almost 1,000 degrees and it won't melt. Here's the same picture in infrared. So what they're doing is they're storing heat energy in sand, and not just in containers like this, but they dig really large pits to get more volume with piping running through it, heat it up. They're getting seasonal heat, heat that lasts for months, and they're doing regional heating of local homes on sand. On sand. So there's so many different ideas out there, and that's our energy future. It's going to come from many different sources, and it's going to be stored in many different ways. Now, here's where you folks come in. Small modular nuclear reactors. Canada's investing in this right now, but there's a huge public fear of nuclear reactors. The word radiation, it's just a trigger word. The word nuclear. And this is where we need education. And one of the scientists that I talked to in my book, he said, the nuclear industry has done a terrible job of explaining itself. They've just kind of been hiding. So don't just trust us. Even though the nuclear industry has the safest record, the best safety record of all our energy production is nuclear. But the public doesn't know that. So we need education to explain how the technology works. And these small reactors are different than the big mega projects. They use different principles, molten salt, pebble beds, whatever. But that needs to be explained to the public, because these things come completely sealed up, made in a factory. You put it on a truck. You take it here in Canada. Our northern communities are now running on diesel generators. And diesel's really expensive, and it's spewing stuff into the air. And you put them underground, so nobody can touch them. This all needs to be explained to the public in terms of how it works, the safety involved, how the radiation is sealed, your job, and do all this. Then we have fusion. Fusion, which is trying to create the sun on Earth. A big project in France right now called ITER is supposedly going to be coming online within the next few years. It's under construction right now. There's a joke in the fusion industry that fusion has been 20 years away for 50 years. But that's one way that they're doing it. The big obstacle is the fact that in order to achieve fusion, you need to heat the plasma up to a ridiculous degree, 150 million degrees. 150 million degrees. That's 10 times hotter than the center of the sun. They got to create that and maintain it. So that's a minor little problem. Massachusetts Institute of Technology has a smaller one using improved magnets called Spark. That'll put out about 300 megawatts. Again, you could power a small town with it. And right here, I noticed right next door on the trade floor, there's our Canadian fusion project called General Fusion. And they take an entirely different approach. They don't need the high temperature, they're using pressure. They're just squeezing the plasma down and using that pressure to create fusion. So energy's everywhere. Energy's everywhere. We have more falling out of the sky in an hour than we use in a year. And all we need is the technology to do that, or excuse me, the will to do that. We're almost there. If we can have good education from the point of the scientists and the engineers on how this stuff works, and convince the politicians that it's a good way to go, and get the public on board, we can do this with energy. We've done it with other technology. Look at your phone. Look at your phone. When I was a kid, before I started dyeing my hair gray, the phone was on the wall. And you had to stand beside it to talk, and that's all it did was talk. Now you carry it in your pocket. Holy smokes, and it can do so many things. Talking is the last thing you do on a phone. This did not come from a government mandate. This came because it was a good product, and everybody bought into it. We've done it with phones. We've done it with music. You can get all the music in the world on your phone now. You don't need a big record player or a phonograph. You can record it. The technology improved, and we all bought into it. We haven't done that with energy. We haven't. So let's move ahead. Let's move ahead and do with energy what we've done with other technologies. I really believe we can do that. I want to leave you just with, oh, this is a crazy idea. Gather a big solar power satellite, huge satellite, gathers the sunlight, turns it into a laser beam or a microwave beam and beams it to the ground. One of those could power a major city, like all of Vancouver here. But I don't know how comfortable people would feel having this big laser beam coming down from space. But anyway, it's an idea. Let me leave you with this idea. I meet really interesting people in my job, and one of them I met was the guy in the white T-shirt, not the fella having a bad hair day in the middle there. I was sitting beside him at a conference when I lived in Toronto, and I said, "Would you like to go sailing tomorrow? I have a sailboat." And he said, "Sure." And I got very excited about that because when I was a kid, I watched Buzz Aldrin walk on the moon. He and Neil Armstrong did the first moon landing. I took Buzz Aldrin sailing. How cool was that? And Buzz is one of only 24 human beings who got to see, where are we, Mike? Oops, sorry, here we are, who got to see the Earth as a whole from another world. They're the only ones who got to see it from another world. And Buzz said, you know, the moon is a really interesting place, but it's not a very nice place. And he's right. The moon will kill you. There's no air, there's no water, you need to wear a spacesuit. And since we went to the moon, we've had robots go out to all the planets in our solar system, and we have now found more than 5,000 planets going around other stars, and they'll all kill you. They'll all kill you. Mars, there's no oxygen in its atmosphere. You have to wear a spacesuit. Planets are either too hot, too cold, too poisonous. Maybe there's another Earth out there, but it's going to be very, very far away from here. So in other words, this is it. This is it. We live in the Garden of Eden of planets. It's the only one you can walk outside and go, ah, nice day. And you're not wearing a spacesuit. There's no other place like it. And this planet's been through a lot. It's been through a lot of changes, ice ages. We've been hit by objects from space. Life survives, but whatever comes back is different than what was there before. So we're at an opportunity now where we can fix this current extinction event that we're living in. The technology's there. Let's get on with it. And if you're interested, there's a bookseller out front that I'll be happy to sign some for you. But I believe we can do it. I believe we can do it. We're smart. We're smart. You're smart. What you do is really smart. So let's convince the world. Give them a sense of hope. Stop pointing at the problem. Let's point to some solutions. Thank you very much for having me here today, and I wish you well. Wish you well.
So we're fortunate to have just a couple of minutes. Does anyone want to ask Bob McDonald a question? Yeah, please, just go ahead to the microphone and introduce yourself and ask your question.
Thank you, Mr. McDonald. This wonderful presentation. And we see from the cover of your book, says the future is now.
Yes.
My question would be, in your presentation, and forgive me because I've not read the book as of yet, you don't mention anything about Canadian can-do nuclear. And I'm curious as to why. My understanding is in Ontario, that accounts for 60% of their current energy. Is it included in your book?
Yes.
And is there a reason that you exclude it from your presentation?
I do list it in the book, and I mention all of the organizations that are against nuclear energy, and I acknowledge them. And we need dialogue. We need dialogue. It doesn't matter if you're talking about nuclear energy or hydroelectric or hydrogen or whatever it is, there are risks and there are costs. And we have to talk about those costs. And we have to come to a reasonable solution, whether or not we're going to go ahead. But I'll tell you about the cost of doing nothing, or the cost of business as usual. They calculated that about 5.5 million people died from COVID over the 2 years that we were fighting it. According to 3 different studies, and I quote this in the book, between 7 and 8 million people a year die from burning fossil fuels, either from air pollution or the effects of climate change. 7 to 8 million people per year. So twice as many people died from what we're doing now than died from COVID. So we can't keep talking about why not to do these things. I don't want to hear arguments about why not to do them. I want to hear arguments about how we can go forward. And I'm not advocating any one of these technologies. I'm advocating for all of them because we're going to need all of them. So yes, you're absolutely right. There's opposition to nuclear. There's opposition to just about everything. There's a new Site C dam going here in BC. There's huge opposition to that. We need to talk about it because we got to move forward. If all we do is talk and argue, then nothing happens, which has been happening for the last 40 years of all these meetings. So I'm not dismissing what you're saying at all. I just don't want to get into argumentative parts about it, that we have to have intelligent dialogue from both sides and find a path forward, whatever that is. Okay?
Thanks.
Thank you for that.
I think it's Julie over there. Go ahead, please.
Thank you. Mr. McDonald, it is a pleasure to meet you. I have been a fan of yours for a very long time. I am a radiation professional, but I am also a PhD student. My PhD deals with science communications, and it's extremely interesting and on point for me what you're doing and what you're advocating for. How can I make this not just an academic exercise? How can we take this further with members of the public?
How can we take it further with members of the public? Education. Education. One of the challenges that I'm facing as a journalist is to distinguish the difference between real science and pseudoscience. Because there's a lot of conspiracy theories, flat earthers, people who have opinions, who are putting out either misinformation or disinformation, and they're really, really good at it, sometimes better than we are. And so there's a challenge there to make sure that the science is forward, that the science gets out, because science is our best tool we have to find the truth, to find the truth. The law used to be that way, but the law turned into who wins. This isn't a case of winners and losers. It's how does this work? So we've got to get the science itself out there, and that's been my job for my entire career, and make sure that the public understands the science and understands the issues so we can make intelligent decisions. Not emotional ones, but intelligent decisions. So that's up to all of us.
So last question, please, go ahead.
My name is Deanna Moscow. I actually remember you from being about that tall watching Wonderstruck. And so it does work, but my question is about that communication is we all represent the nuclear industry in some way. So when we speak, there's this inherent perception that we are biased to the thing that's paying us. You have that beautiful position where you sit in between both sides. How do we contradict or present information in a way that won't be inherently considered biased because of where our paychecks come from?
Okay, so that's a very good question. I suggest you start with young people. Start with young people, because in order to explain something to a kid, you've got to keep it real. And I find when I'm talking with young people, you start with something familiar that they're used to and then go into the abstract, whatever the subject is. But also take those young people, tear the devices out of their hands, tear them away from their computers, rip them away from their overprotective parents, take them out to a forest or a river and shove their face in the dirt. Turn over some rocks, see what's crawling around underneath them, introduce them to planet Earth, and say what a remarkable place this is. And then start talking about how we got to keep ourselves warm, how we move from here to here to there. Why are electric cars better than combustion cars? How does a combustion engine work compared to an electric motor? How does nuclear energy work? How does it actually work? Where does radioactive fuel come from? Gee, it comes from the Earth. You know why the Earth is warm? It's because of radioactivity. And explain to them the whole process from the beginning to the end in a non-threatening way. Then, when they become the decision makers, they've got the education. We've got to keep the youth, got to keep the young people informed, because they're the future politicians, the future scientists, the future business people. And I find that the youth are overwhelmed with dysfunctional marriages coming out of Hollywood, drug-addicted musicians, fashion and products and things. I mean, we all need sex, drugs, and rock and roll, but let's teach them a little science along the way as well. So start with the youth, okay?
Excellent. Thank you very much, Bob. One more round of applause, please, for Bob McDonald.
Thank you very much.